Yeah.
Yeah.
Okay, my name is Volodymyr Linik. I'm your teacher in this course of nonlinear systems. And today we solve some exercise, and do some exercise and try to calculate something in MATLAB. I hope all of you have MATLAB on your PC. And one moment. Okay. Today we start with nonlinear systems, phasor portraits, and stability. As I say, my name is Volodymyr Linik. I am from Department of Control Engineering, and my research interests include, but not limited to, chaotic dynamics, chaos-based communication system, chaos-based random generators, complex networks, multi-agent systems, adaptive observers, or biological systems. And if someone of you want to do some semestral work, or for example, I can supervise some master thesis. Okay. First for all, I want to repeat something about dynamical systems, what you listen on the previous lecture from Professor Chirikovsky. The dynamical systems is right like in the next form, x1 dot equal to some function from t, x1 xn and u1 um, and the x2 dot equal to f2. This function is from depend on t, x1 xn, u1 um, and so on, and where xe dot denotes the derivative of xe with respect to the time variable t, and u1 um are input variables, x1 xn are the state variables, and we usually use vector notation to write this equation in a compact form like this. Define x equal to x1 xn transpose, u equal to this vector transpose, and the function txu equal to this vector function transpose, and rewrite the n first order differential equation as one n-dimensional first order vector differential equation. X dot equal to f from txu, and we call that 2, equation 2, the state equation, and refer to x as a state, u as an input. Sometimes another equation, epsilon equal to h, y equal to h from txu, is associated with 2, thereby defining a q-dimensional output vector y. Okay, special form of the state model. For linear systems, the state model 2-3 takes a special form. A special case of 2 without explicit presence of an input u, the so-called unforced state equation, is equal to x dot equal to f tx. Okay, nonlinear phenomena. For example, it's finite escape time. The state of an unstable linear system goes to infinity as time approaches infinity. A nonlinear system states, however, can go to infinity time. For example, on the lecture, Professor Tchaikovsky showed you some example, and multiply isolated equilibria. A linear system can have only one isolated equilibrium point, thus it can have only one steady state operating point that attract the state of the system irrespective of the initial state. And a nonlinear system can have more than one isolated equilibrium point. The state may converge to one of several steady-state operating points, depending on the initial state of the system. Okay, limited cycles for a linear time-invariant system to oscillate. It must have a pair of eigenvalues of the imaginary axis, which is a non-robust condition that it is almost impossible to maintain in the presence of perturbation. Even if we do so, the amplitude of the oscillation will be dependent on the initial state. In real life, stable oscillation might be produced by nonlinear system. Okay, and some another subharmonic, harmonic, or almost periodic oscillation on chaotic chaos and multiply modes of behavior. Okay, two-dimensional systems. A two-dimensional time-invariant system is represented by two differential equation x1 dot equal to f1 from x1 x2 and x2 dot equal to f2 from x1 x2. Let x from t equal to x1 t x2 t be the solution of 5, and that starts at x0, and the locus is the x1 x2 plane of the solution xt for all t greater than 0 or equal is a curve that passes through the point x0, and this curve is called the trajectory of orbit of 5 from x0. The x1 x2 plane is called the state plane or phase plane. Using vector notation, we rewrite 5 as x dot equal to f from x, where f from x is a vector, and we consider this vector as a vector field of the state plane. In deriving the vector field at every point in a grid covering the plane, we obtain a vector field diagram. Okay, do you have any question at this moment? You can ask if you want, yeah. Okay, first portrait. Let's let a second order linear system described as the next equation. x2 dots plus r1 x dot plus r2x equal to 0, or in a normal form x1 dot equal to x2 and x2 dot equal to minus a1 x2 minus a2 x1, and the solution, phase portrait, and tips of the crucial points are dependent on the roots of the characteristic equation lambda 2 plus a1 lambda plus a2 equal to 0, and the system 7 has one equilibrium point in the origin. The behavioral stability or stability of these equilibrium points is dependent on the phase portrait on the neighbors of the crucial point. For example, here you can see the classification of crucial points. An equilibrium point to a system is said to be isolated if there is a neighborhood to the crucial point that does not any other crucial points. There are 4 different types of isolated crucial points that usually occur at center. Here I haven't this center. I show you this kind of equilibrium point on the MATLAB simulation. Yeah, center node this one. This is a stable node because you can see that arrow goes to 0. Yeah, all this, and it's possible if real path two eigenvalues is have the real path less negative. Yeah. Okay, settle. is if one eigenvalue is positive and one negative, it's unstable kind of equilibrium point. Then this is unstable node when both of eigenvalues only real part is positive, and this is unstable focus when real part of complex eigenvalues is positive, and here is an unstable focus when the real part of the complex eigenvalue is negative. Okay, multiply equilibria. Nonlinear. Do you have some question here? Yes. I put this presentation to Moodle. Yeah, and you can download, and I add this center here because here we haven't this stable point center. Center is a type of equilibrium point when two eigenvalues has only complex, only imaginary part of the eigenvalues. Yeah, real part is equal to 0. Okay. Multiply equilibria. Nonlinear system should include several equilibria. Let's find and characterize equilibria of the next nonlinear system. X1 dot equal to minus x1 and 1 plus x product 1 plus x1 squared minus 2x2 and x2 dot equal to x1 plus x2. Then let x1 dot equal to x2 dot equal to 0. When we want to find the equilibrium point, we need to take x1, this x1 dot and x2 dot equal to 0. Yeah? And then this equation, this system has 3 solutions. X1 equal to 0, 0, x2 0, x1 1, x2 minus 1, and x1 equal to minus 1, x2 equal to 1. If you put this here, you found that this is 0 and it's true. Yeah, and okay, near the first, and now we need to analyze the behavior of this equilibrium point, or the behavior of this near this equilibrium point. Near the first equilibrium point origin is 0, 0, its origin. Then linearized equation has the next form: x1 dot equal to minus x1 minus 2x2 and x2 dot equal to x1 plus x2, and we calculate Jacobian. Yeah, and this is a Jacobian from original equation. Yeah. We calculate this Jacobian from original equation, and then we put this 0, 0 here, only 0, yeah, and found that matrix A equal to this Jacobian is equal to minus 1, minus 2, 1, 1, and found the eigenvalues, and found that lambda 2 plus 1 equal to 0. It's lambda 1, 2 equal to plus minus g. Therefore, this equilibrium point is a center. Yeah, but this is only linear approximation. We can say that only in near this point this system have this behavior, but okay. The next, do you have some question here? Okay. Multiply equilibrium second case, near the second equilibrium point, 1 minus 1. The linearized equation has the same form, yes, and we put this 1 here, yeah, and found that lambda 2 plus 3 lambda minus 2 equal to 0. We need to solve this characteristic equation, and when we solve it, then we found that lambda 1, 2 equal to minus 3 plus minus square root of 17 and divide 2. Yeah, and in the first case it's positive number, and for the second it's negative. Yeah, and therefore this equilibrium point is a saddle point, is unstable, one positive and one negative. Okay, the next one is the same, because we can see that x1 squared, yeah, and if we put this minus 1 here, yeah, we found that the same characteristic equation and the same value of lambda 1 and lambda 2, and therefore this equilibrium point is a saddle 2. Any question here? Okay. And first portrait of a system of orders, undamped pendulum with no driving force is described by the next equation: x2 with 2 dots plus sinus x equal to 0. And let the reduce equation to a standard form of the system of first order orders by letting x1 equal to x and x2 equal to x1 dot. Then x1 dot equal to x2 and x2 dot equal to minus sinus x1, and the first portrait is a plot of a vector field with which qualitatively shows how the solution to these equations will go from a given starting point. Okay, to generate the first portrait, we need to compute the derivatives x1 dot x2 dot at t equal to 0 and on a grid over the range of values for x1 and x2 we are interested in, and we will plot the derivatives as a vector at each x1, x2, which will show you the initial direction from each point. We'll examine the solutions over the range from -2 to 8, and for x1 and for x2 is from -2 to 2, and create a grid of 20 and 20 points. And then we need to compute in the vector field. We need to get two metrics U and V. Okay, and then this command KYR to plot the vector field can be used in MATLAB. Here we have some MATLAB code, yeah, adopted from this web, and now I can show you how. I can show the vector field. Okay. I don't know if I can share this MATLAB code directly in the Microsoft Teams. Okay. Okay. Now I show you how we can calculate this or make this vector field of the pendulum without friction. Okay, I only check. Okay. Okay. Can you see this figure? Okay, okay. This is a problem with, I think this is a problem with this Teams. I need to always choose this figure because it's some another window. Yeah, and now,
Yeah, there is that option. You can show the screens or the windows.
okay, okay, okay. But now you see this figure? Yeah, okay. And can you characterize this equilibrium point here? Only from this vector field. Yeah, you show this is the one equilibrium point here in 0. Yeah, one here is it's I think 2p and one in p. Yeah, and can you say something about this equilibrium point? Okay, this equilibrium point is centered because you see that when we start here, we always go stay here, yeah, in this circle. But here it's a separatories because when we start, for example, here on the top, yeah, we go out and do not stop. Here is a saddle point because you can see that some arrows goes in this point and some go out of this point. Yeah, this is characterize negative eigenvalues. This here, yeah, and this characterizes this positive eigenvalue. Yeah, okay. And now I try to start with I uncomment. Okay, now you see this figure, yeah, the same figure, but with I try to simulate several different 5 different initial condition. Yeah, you see this figure with from MATLAB. Sorry, moment, and now number 1. Okay, okay, and we can start with solution. For example, we can choose some initial condition, x1 equal to 0 and x2, for example, equal to 0, and we stay in this 0. Yeah, you can see. If we choose, for example, this, I don't know, for example, 0.5, yeah, we stay on this orbit always. Yeah, and so on. When you want 1, x1 equal to 0, x2 equal to 1, and this stay on this circle. Yeah, this is a stable point, and here the same, and always when we start we always stay on the same orbit. Yeah, and but when we start here we go to this saddle point and then make one more step and go out. Yeah, and this is here you can see that it's this is when we start with this point, it's a problem. because we go to unstable point, unstable equilibrium, and then go out, and if we start with more time, yeah, it's go fast away. Yeah.
Excuse me, one question.
Yes.
I didn't got it correctly. So is this figure also related to the pendulum example, or?
Yes. This figure is related to pendulum example, because here you can see this equilibrium point of 0, 0, 0 p and 0 2p. Yeah, this one in 0, 0 is stable. This is center because 2 values plus minus g, as we solved on slide. Yeah, and here the same. Yeah, because here is the same, is the center, but this point 0 p or 0 to p, yeah, is unstable. Yeah.
May I have comment?
Yes.
Yeah, this is Sergei Chelikovsky speaking. Lecture. It's a little bit confusing that actually all these equilibria, which are repeated 0, 2 pi, and 4 pi, they are the same physical equilibria, right? So pendulum is heading below. And these other pi, 3 pi and so on, is unstable position pendulum upward. But it's good to have these many representation of the same position, because when you go above these separatrices, it means that pendulums start to rotate. It is so quick that it rotates like circularly around. And then if you are, say, in 4 pi, 6 pi, then you somehow counted how many rotations you did make. Yeah. So maybe this is kind of explanation why you have so many representation of physically the same position of equilibrium. Yeah. So so actually, what you see, the equilibrium like 2 pi, yeah, then it is again equilibrium below. But if you are there, it means that you somehow make more rotation. Of course, in this case of without friction, you cannot go from this equilibrium to another. But later on, I think when you show this damped pendulum, then it will be clear that you may somehow rotate, and then you, when frictions slow down, then you start oscillate like pendulum, and then the sector where you finish denotes somehow how many rotations you did make before, yeah, before you started to stabilize. Okay, that's it. I will not further interrupt you.
Okay, thank you, Sergey.
Thank you.
Okay, and now I will show you. Moment, I need to find. Okay, now I can show you the same pendulum but with friction, and I need to change this moment. I want to find. Okay. Okay, now you can see the vector field of the pendulum with friction. not only minus sinus x1, but we minus 0.3 x2. Yeah. This example is from Khalil book, yeah, example 2.3, yeah, and you can see that if we start, for example, here we go to the equilibrium point, and when we start here we go to equilibrium point, but we can try to start with, for example, with another initial condition and try to go to another equilibrium point, because here's the same. We have stable node, stable focus here, and saddle point. One moment, I try to enlarge this figure and try to add one more initial condition. For example, try this one. No. Okay. Okay, here you can see that I start with initial condition equal to 3, x1 equal to 0, x2 equal to 3, and then the pendulum make one rotation and then go to 0. One full rotation. Any question here?
So does it mean that the yellow line is that you made the pendulum to swing so much that it ran over the unstable position and then
yes,
that settled down, like heading downwards?
Yes, exactly.
Yeah. Okay. Thanks.
Okay, and then this pendulum make one rotation and then go to this stable. Okay, now sorry, moment. Now we come back to the presentation. Yeah, this one. Okay, this is a MATLAB code. I put this MATLAB code to Moodle, and you can try at home. Different analyzed different systems. Yeah. Okay, multiply equilibria. For example, this is a next example from Khalil book. This is a state model of the tunnel diode circuit is given by the next equation. Sorry, this is. Assume that circuit parameters can be found in Khalil book, and according to this parameter, the state model is given by the equation 16, x1 dot equal to 0.5, and then minus this function h from x1 plus x2 is a function f1 from x, and defines it a function f1 from x, and x2 dot equal to 0.2 in this expression, and it is defined as f2x, and suppose h is given by the next equation, and let x1 dot equal to x2 dot and equal to 0, and then there are three solutions of this. The equilibrium points are determined by the intersection of the curve x2 equal to h from x1, and with the load line 1.5 x2 equal to minus x.1 minus x1, yeah. And for given numerical values, the two curves intersect at the three point 1, this one, q1 is 0.063 and 0.758, and q2 the next, and q3. Yeah, and the equilibrium of the matrix of F is given by the next. Yeah, and where x the derivation of function h equal to 17.76, and so on. Yeah, and for each equilibrium point, evaluating the equilibrium matrix at the equilibrium points q1, q2, q3 respectively yields a1 equal to the next matrix a1, a2 is correspond to q2, and a3 is correspond to q3, and the eigenvalues here is negative, here 1 negative, 1 positive, and here is both eigenvalues are negative. This is, it means that this q3 equilibrium points is a stable node, q1 is the same, the stable node, and q2 is a saddle point, unstable point. And now okay, now I show you in MATLAB. This moment, I need to find MATLAB. Okay, and okay, here you can see on this figure 1 the vector field of the tunnel diode circuit of the example. Yeah, here this equilibrium point is q3. It is a stable node. Yeah, here you can see that maybe here it's saddle point. Yeah, and it's q2, and here this equilibrium point is Q1 is a stable point, is a stable node. Any question here? Okay. Let's come back to presentation. Okay, multiply equilibria. The next, this is the pendulum with a friction, and I show you in MATLAB the vector field of this pendulum with friction of this model, and okay, x1 dot equal to x2, x2 dot equal to minus sinus x1 minus 0.3 x2, and the Jacobian matrix is given by A is equal to this matrix, and we know that pendulum has equilibrium points in 0, 0 and P0, respectively, and this is 0, 0 point, and this is 0, P0 point, and the values of this first is a real part is negative, and this is a complex number, and with negative real part, and here two eigenvalues, one positive and one negative. And I show you before in MATLAB that this type of equilibrium point is a focus, stable focus, and this is a saddle point. Okay, and now do you have any question in this material? Okay, and now okay, and now I show you the stability. I will talk about stability of equilibrium point, the first Lyapunov method of the so-called indirect Lyapunov method, and the problem. The first Lyapunov method considers the n-dimensional system x dot equal to f from x. Let Gx be a Jacobian matrix of f from x that is this equal to this one. Okay, and theorem from Khalil book 3.2, let x equal to 0 be an equilibrium point for the nonlinear system x dot equal to f from x, and let A this is Jacobian in 0, and denote its eigenvalues by lambda 1 to lambda n, and then the origin is exponentially stable if and only if real part of eigenvalues less than 0, negative, and the origin is unstable if real part of eigenvalues are positive for one or more eigenvalues. And now let's analyze this system 1 x. This is a nonlinear system. x1 dot equal to 2x2 cubed minus x1 5 in 5, and x2 dot equal to minus x 1 minus x2 in 5. And we calculate Jacobian of this. Take the partial derivative of this f1 of x1 is equal to minus 5x1 4, yeah. Then make the same for on x2, and this is 6x2, yeah. 6x2 squared. This is I think error here. Yeah, and here minus 1, and here is minus 5x2 in 4. Yeah, and then put 0. Okay, here is a typo here, but the result is the same, because all this x1 and x2 equal to 0, and then we need to find eigenvalues, and okay, then determinant a minus e lambda equal to 0 minus lambda, 0 minus lambda, 0 minus 1 equal to 0, and then calculate minus lambda product minus lambda minus 1 product 0 and equal to 0, and lambda squared equal to 0, and then lambda 1, 2 equal to 0. Okay, can we say something about the stability of this system depend under the first Lyapunov method? We can't say anything about the stability because equal to 0, and in theorem 3, 2, the region is experimentally stable if and only if real part of eigenvalues is negative for all eigenvalues. Yeah, and we can say anything here. Yeah, and we can try to use the second Lyapunov method, but we do it on the next exercise. Yeah, on the next lecture, on the next time. Yeah. Okay. The second example is a test the stability of the next linear system x with 2 dots plus x dot cubed plus x equal to 0. Rewrite system in the state space form. Okay, x1 dot equal to x2, x2 dot equal to minus x2 cubed minus x1, and then we calculate Jacobian. Is 0, 1, yeah, x2 is 1, and here it's minus 1, and minus 3 x2 squared, yeah, and then we put 0, this x2 equal to 0, and then matrix A has this form, and now we need to calculate eigenvalues. Okay, minus lambda minus and okay, lambda 2 plus 1 equal to 0, and lambda 1, 2 equal to plus minus g or e is a complex number without real part. And can we say something about the stability here? It is a question for you. Can you listen me? You hear me?
Yeah, we can hear you.
Okay. Okay. Here we can say anything about the stability, because in linear system, this is a stable. In a linear system, this point is a center, but in non-linear system, we can say anything, yeah, about the stability of overall system. Yeah. Okay. The next example is x1 dot equal to x2 minus x1 cubed, x2 dot equal to minus x1 cubed minus x2 cubed. Yeah, and the same, we need to calculate Jacobian. Yeah, we calculate Jacobian and found that eigenvalues is equal to 0, and we can't say anything about this system with a first Lyapunov method or with indirect Lyapunov method. Yeah, we need to use the second Lyapunov method, but we apply this method in the future. Yeah. And the next is 4. The next example is x1 dot equal to minus x1 minus x1 cubed. Yeah, can you say anything, something about the stability of this system? Yeah, should be stable, because depend on the theorem of 3.2 from Khalil, the origin exponentially stable if and only if real part is negative for all eigenvalues. Here we have only one eigenvalues, and this eigenvalue is equal to -1. Yeah. And okay, this system is globally stable or locally, only locally? Okay, when we apply the first Lyapunov method, or this indirect Lyapunov method, we only prove in nonlinear systems, only prove the local stability. Because, for example, here this system is global exponential stable, yeah, because this minus x1 cubed is a stable system and global exponential stable system. But if, for example, we choose x1 dot equal to minus x1 plus x1 squared or cubed, what we say about system if we change this x1 squared minus 2 plus, for example? This system is stable or not? Okay, if we apply the first Lyapunov method or indirect Lyapunov method, we can say that this system x1 plus x1 cubed is a local exponential stable, because here only one eigenvalue with real part, with negative real part, and when we start near the equilibrium or near this origin 0, 0, then the solution will converge to the 0. Yeah. but we can say anything about global behavior of this system when here it's plus x1 squared or cubed. Sorry. One moment. I try to find this. Yeah. Okay. Yeah. Here, this equation, example number 5. It's what I say before. Yeah. If you have this plus x1 cubed, then system is local exponential stable in all region, and to prove the global exponential stability or asymptotic stability of this system, we need to apply a second Lyapunov method or direct Lyapunov method, yeah, and so on. Okay, the next example is a linear system. Is a approximate linearization of
Your microphone is switched off. I'm sorry to interrupt you, but I can't hear you.
And now you listen me?
Yeah. Now I can hear you.
Yeah, okay.
Yeah, now it's.
Yeah, sorry. One moment. Okay, here, this example number 6 is a linear system. x1 dot equal to x2. You hear me? Yeah.
Yes, I can hear you.
Okay. x1 dot equal to x2. x2 dot equal to minus x1. This is linearization of pendulum, and we can apply this
We cannot hear you anymore. And now, yes.
Yeah.
Now,
I don't know why, but sometimes it's switch off. Yeah.
okay, but it's on now, so it works.
Yes. Okay. And I come back to presentation. Sorry, not presentation, but okay. And now you see now this this equation, this example 6.
Yes, yeah. Number 6. Yeah.
Number 6. Yeah. Okay. This is a linear system. This is approximation of pendulum equation. x1 dot equal to x2, x2 dot equal to minus x1. Yeah, this is approximation of pendulum. It's linear. Yeah, and we can apply this indirect Lyapunov method and found that lambda 1 2 equal to this complex value.
Excuse me. It's the approximation for small angles, or
yes,
is it?
yes. This
okay.
Approximation of small angles, because when you know that sinus in when you use Taylor expansion, you know that you can find that this is small angles, maybe near, I don't know, 12
degrees or
degrees, yeah, 12
okay.
degrees. Yeah.
Okay, so it's around some operating point or something like that.
Yes.
It's
And
the point 0, 0. It's the like
yes,
the
it's point
position
0, 0.
heading downwards.
Yeah.
Okay.
Yeah.
Okay. Thanks.
And you can find that this lambda 1, 2 equal to complex value without real part. Yeah. Yes. It's center. Yeah. And I show you before on MATLAB simulations that in a normal in the pendulum without friction we can start and then we stay always in some circle. Yeah, this is a stable system here. Yeah, and in our case the system is linear system, and therefore the system is local Lyapunov stable, but not only local but global, because when it's only approximation here, yeah, and only one equilibrium point here, 0, 0, yeah, and this global Lyapunov stable, or global stable without Lyapunov. When lambda 1, lambda 2 equal to complex value without real part, then this system is stable. Not Lyapunov stable, but only stable. Yeah. Okay. The next example is this one: x1 dot equal to x2 minus x2 squared, x2 dot equal to minus x1 plus x1 x2. Yeah. And we calculate Jacobian here, yeah, in equilibrium point 0, 0 in origin, and we found the eigenvalues, the same eigenvalues plus minus g as in example 6, but in this case this system is not nonlinear, and we can't say anything about the stability of this system. Yeah. Any question here?
So when the system is nonlinear, then we can say nothing about like the general or global stability of the system, but does this the mentioned or the written equations, does it describe at least the stability of the system at that point properly, or
yes, at point?
Yeah, so it's valid for the point.
Yeah, it's valid for the point. But for example, in test or on exam, always you can read that you need to found the stability of this, to prove the stability of the system in origin, for example. Yeah, only in origin, because some system has more points. Yeah, and you don't need to analyze all these points, but only this origin. And but now we only apply the indirect Lyapunov method, and it works only if we can say, okay, if real part is negative, then this system is local stable. If real part positive, yeah, for example, one eigenvalue positive, one negative, it is a saddle point, and then we can say, okay, this system is unstable in this point, and therefore and therefore we need to apply the second Lyapunov method. And
okay, so when the system is unstable at some point, then it might be stable in a different one, like
yes,
it is
yes,
nonlinear.
yes. Yes, for example, in this tunnel diode circuit, 2 points are stable nodes and one is unstable. Yeah, and when we start on some we can go to some of this stable point, and if we want to analyze this system by the first Lyapunov method, we only know that if we apply the indirect Lyapunov method on the nonlinear system and found that lambda 1, 2, for example, equal to plus minus g, then we need to apply we need to apply direct Lyapunov method. That's all. We can't say anything about the stability of this system besides on this lambda 1, 2. Okay, and the next example is a pendulum x1, x2 dot equal to minus sinus x1 without friction. And here you ask me about this linearization, and I think the angles axis 1%, it's 14 degrees, and we can in our case the system nonlinear one, and we can't say anything about the stability, and we need to apply the second Lyapunov method. And the alternative way for linearization is using the Taylor series for the linearization of the original nonlinear equation, and where the sinus x equal to x minus x cubed divide the 3 factorial, and these high order terms go out, and only this x stay. Only this linear part. Okay. And the next example is x1 dot equal to x2 cosinus x1 and x2 dot equal to sinus x1. Equilibrium points are kp 0, where k is a z, and linearization is the next. We make linearization if in 0, 0 is equal to this matrix 0, 0, 1, 1, and when we found the determinant and lambda 2 minus 1 equal to 0, and lambda 1, 2 equal to plus minus g, and these points origin is unstable because maybe some error here.
I'm sorry, shouldn't it be plus minus 1 instead of plus minus y? Because it's lambda squared minus 1 equal to 0.
Yes. Here is a typo or error, maybe a copy from this one, and lambda 1, 2 equal to minus 1 and plus 1, is a saddle point here, because lambda 2 equal to 1, yes, it's correct? No?
I believe so.
Yeah. Yeah, lambda 2 equal to 1 and lambda 1, 2 equal to plus minus 1. Yeah, not e but 1. And this origin is unstable because it is a. Okay. The next example 10, x1 dot equal to minus x1 cubed plus x2 dot equal to minus x1 cubed minus 4x2, and we calculate a Jacobian. This is minus 3x1 squared 1 minus 3x1 squared minus 4. Okay, in 0, 0 is equal to lambda 1 equal to 0 and lambda 2 equal to minus 4. It's mean what? Can we say something about the stability of this system based on the first Lyapunov method? Yes, exactly. Here we need to apply the second Lyapunov method because when we apply only this indirect Lyapunov method, we can say anything about this system, yeah, because 0 and minus 4. Okay, the next example is x1 dot equal to x2 plus x1, x2 dot equal to minus x1 minus x1 squared. Okay, we calculate Jacobian, and in 0, 0 it has the next form, and we found the eigenvalues. I think it's correct. Yeah, it's plus minus g in the same problem, because in our case this system is nonlinear, and when we apply the first Lyapunov method, we can say anything about the stability of this system in this point. Okay, and we need to apply the second Lyapunov method. Example number 12, x1 dot equal to x1, 1 minus x2, product 1 minus x2, x2 dot equal to minus x2, and 1 minus x1, and we need to find the equilibrium points. This is two equilibrium points, 0, 0, and 1, 1, yeah, and we calculate Jacobian, and for 0, 0, it's equal to the next matrix, yeah, and found eigenvalues. One eigenvalue is positive and one is negative, and it is a saddle point, yeah, this equilibrium. And now we found eigenvalues in the second equilibrium point, 1, 1. Okay, we calculate and put this 1, 1 here, and now we found that lambda squared plus 1 equal to 0, and lambda 1, 2 is equal to plus minus e. And can we say something about this, if this stable or unstable? We know this equilibrium point is at center, but can we see something? Okay, we can, because it is nonlinear system, and can say anything, and when we need to apply the second Lyapunov method. Yeah. Okay, the next example, x1 dot equal to 1 minus x1 squared, x2 dot equal to x1 x2, and we found equilibrium points of the system. first is 1, 0, and the second one is minus 1, 0. Yeah, and when we calculate the eigenvalues, we found this first one is lambda 1 equal to minus 2 and lambda 2 equal to 1. Yeah, this equilibrium point 1, 0 is a saddle point, yeah, and it's unstable. The second one is minus 1, 0, and we calculate Jacobian, the same procedure, and minus 1, 0. Here is a mistake because it's without minus, and then we found that lambda 1 equal to 2 and lambda 2 equal to, I think here some mistake, yeah, and maybe it's plus 1 or okay, minus 1 minus 2, yeah, and lambda 1 is a 2 and lambda 2 is a 1. Yes, and this is unstable, not a saddle point, or I need to check this example, sorry. And test the stability of the next linear system, x with 2 dots minus x plus x cubed equal to 0, and the right system in a state space form, x1 dot equal to x2 and x2 dot equal to minus x1 plus x1 cubed, and equilibrium points are first 0, 0 and second 1, 0 and third minus 1, 0. Yeah? And then we apply indirect Lyapunov method, this first Lyapunov method, and for equilibrium point 0, 0, the eigenvalues equal to plus minus g, and therefore this is centered by, we can't say anything about the stability of the overall system. And let's analyze the next equilibrium point, and we found that this equilibrium point is a saddle point because eigenvalues is equal to plus minus the square of 2, and therefore this is a saddle equilibrium point, and the third equilibrium point is the same because he has the same eigenvalues, and we need to apply the second Lyapunov method, and then we can say something about the stability of this system. Okay, 15, x1 dot equal to 2x1 minus x1 x2, and x2 dot equal to 2x2 minus x2, and equilibrium points in 0, 0 and plus minus 1, 2, and we calculate Jacobian, and that found the eigenvalues correspond to the first equilibrium point. It's lambda 1 equal to 2, lambda 2 equal to minus 1 is a saddle point, unstable, and the next point is 1, 2, yeah, and when we calculate, we found that lambda 1, 2 equal to minus 0.5 plus minus 2g. Can we say something about this point? What kind of stability or what kind of point? Yes, it's a stable focus. Yeah, because this is a local this system is local, exponential, stable at this point 1, 2, yeah, and this one, because the real part of the eigenvalues is negative, yeah. Both eigenvalues has a real part negative, and the next we analyze the next equilibrium point -1, 2, and
The microphone is off once again. Not working anymore. Now it looks like it's working once again.
okay, and I hope you see this.
Your mic is again switched off, Volodymyr. Now it's okay.
Okay.
You can watch it in these small windows with your name, where sometimes appear.
Oh, but well, yeah, yes. Okay, and now, okay, here's this equilibrium point is a stable focus. This one, 1, 2, and the next one -1, 2 is a focus 2, yeah. And therefore, these two equilibrium points are focus points, and these points are exponentially stable. And note that all coefficients of the characteristic equation are positive here, yeah, and then the system is asymptotically stable in the local equilibrium points. And the next example, x1 dot equal to x2 minus 2x1 cubed, x2 dot equal to -4x1 minus 3x2 cubed, and we apply the indirect Lyapunov method and calculate the Jacobian. And in this point 0, 0, it's equal the characteristic equation lambda squared plus 4 equal to 0, and therefore lambda 1, 2 is equal to plus minus 2g, and we can say anything about the stability of the system under the first Lyapunov method. Yeah, and we need to use the second Lyapunov method to prove or to testing the global asymptotical stability or exponential stability of the system. And the next example is x1 dot equal to minus x1 cubed minus x1 x2 squared, and x2 dot equal to minus x2, and we apply indirect Lyapunov method and calculate the Jacobian. And in the origin, the eigenvalues equal to lambda 1 equal to 0 and lambda 2 equal to -1, and we can say anything about the stability of this system based on the first Lyapunov method. And we need to use the second Lyapunov method. And the next equation is x1 dot equal to x2 plus ax1 cubed, x2 dot equal to minus x1 plus ax2 cubed, and we calculate Jacobian, and we can find that lambda 1 2 equal to plus minus g. We can't say anything. Yeah, and here I have some. This is for direct level method. And okay, do you have any question? Yes. Yeah, second method is about function. Yes. Yes. We apply the second Lyapunov method on the next exercise, next time, because now we only start and only analyze the equilibrium points and the stability of the system based on the first Lyapunov method.
May I add something? Just to the first method of Lyapunov. If all real power eigenvalues are negative, we may conclude about local asymptotic stability. If there is at least one real power positive, just one, then we may claim it is unstable. And undecided cases are if there are either zero real parts and some negative part. So then you cannot say nothing. So it's not necessary that all of them are zero to have this undecided case. Yeah, or all of them positive to say that it's unstable. So to have unstable, just one is enough to exclude. To have stability, all of them have to have negative, and the rest is undecided. Yeah, okay, it's a very difficult question. We will have it in future lectures. And of course, this basic result is again that you may guarantee some very small neighborhood. But then we will discuss some method where at least sometimes we can give some estimate of this neighborhood where it is asymptotically stable. But in general, first method of Lyapunov just guarantees some not only small, but small in an undefined size. Yeah. So again, this kind of mathematical formulation, there exists some delta greater than zero that in delta neighborhood of zero it is asymptotically stable. Yeah, but we will address it in detail. This is just some preliminary exercises, and detailed theory will be, I think, in 2 weeks maybe. Okay, thank you.
Okay, I think if you have any question, you can ask me or you can send me a mail. Yeah, and see you next week. Thank you.